Hey everyone! Today's adventure is building a video frame classification system courtesy of Google Cloud and a wonderfully low-code method. Let's jump into some of the key concepts so you can grasp the idea before we dive into the hands-on tutorial. Picture this. We have video assets and configurations tucked away in Google Cloud storage. What next, you ask? We need a video processing solution like running pipelines in Vertex AI, which will finish out frames from these videos and store them in the same bucket. Out of the bucket, we pull videos, and into the bucket, we push frames. A perfect circle of video to image transformation. While we're using Vertex AI pipelines here, you could just as easily use services like serverless Spark or Cloud Functions. Moving on, the frames are now leveraged in an AutoML pipeline, which is also a part of the Vertex AI system. More than just no-code model training, we can use AutoML for inference, data management, model evaluation, testing, and labeling work. For the supervised training, though, our video frames need annotations, so we'll invite our team, or ourselves, to waltz in and handle that labeling through the Google Cloud Console. Today's video is from Google Cloud Sample Data, a Jane Goodall video with forest and primate shots. For a fun use case, let's identify frames showcasing a monkey, training our AI model to differentiate monkey-filled frames from boring monkeyless frames. Sounds exciting? Let's wget the video file, then use gsutil to copy it into our new bucket. For the frame extraction pipeline, let's fire up the Cloud Shell editor and walk through our pipeline definition task. No need to furiously type along. We'll share this code in the video description. Now here's where Kubeflow, a Vertex AI compatible open source pipeline framework, takes center stage. We can create a solid pipeline with just a few dozen lines of code. As inputs, we're using a video file path and an import file path, with the latter essentially being a catalog of our images for use as a delimited JSON training specification. We've teamed up with the OpenCV library to extract frames and to keep our dataset size manageable by only yanking one image per second. Training on every single video frame is typically unnecessary. To specify the extraction of a frame every nth second, rather than extraction of every nth frame, you'll need to use the frame rate of the video. Each frame is written as an image file to cloud storage, building up our training dataset. In our pipeline specification, we're looping through our videos and assigning one task per video. For this video tutorial though, we'll keep the video list small. Feel free to add more videos if you're following along. Anyway, let's go ahead and define the Jane Goodall video file, install the Kubeflow Pipelines framework, compile the pipeline, and voila! All compiled and ready to go. Let's upload this compiled pipeline to our bucket, paving the way to run the frame extraction. Before running the pipeline, let's remind ourselves of the broader context. Go to Vertex AI and enable the recommended APIs. AutoML builds off the Vertex AI datasets. To improve performance, we'll co-locate our dataset with the US multi-region that we use during bucket provisioning. For example, the US Central region should work. AutoML features a variety of classification and segmentation tasks, but for our tutorial today, we'll keep it simple and stick to a single label image classification. We'll decide whether the entire frame has a monkey in it or not. Now we finally reach the point where we need that import file and our extracted frames. So, without further ado, let's run the frame extraction and import file compilation pipeline in Vertex AI. We'll import specification from cloud storage and stick to our trusted bucket for the pipeline run output directory. Now, we just have to wait patiently for the pipeline to wrap up. Our first attempt stumbled over a pesky error. Bucket is not defined. But don't fret, this is good practice. Here's the rub. This variable, defined at the root level, isn't making it into our pipeline components. So let's hardcode our bucket throughout the specification. Admittedly, this is not the most elegant solution, but given the circumstances, it will certainly bandage up the issue. Next up, we just need our reliable GS-util copy to set up the new pipeline specification file. Armed with that, let's test our luck and fire up the pipeline once more. With a triumphant pipeline run, we've got ourselves the import file path and a treasure chest of images needed for training our AI. All of the images are tucked away neatly in folders that match the associated video names. Looks like we've got a sizable bounty, 163 images paired with an associated import file. Onward to the next task, getting the Vertex AI dataset populated. With 163 images, our import will be relatively quick. Keep in mind, though, importing larger sets of data might take quite a bit longer. Now brace yourselves for a task requiring some patience, labeling all these images. Once upon a time, a labeling service existed that you could utilize equipped with a team of labelers from Google. Sadly, it's an era past as the service is now deprecated for new users. So roll up your sleeves because you're going to get your hands dirty labeling through the console. You can select the labels you want, like contains monkey and its opposite, monkeyless. Now comes the fun part, scrolling through our images and labeling them in the console. It looks like our first image is devoid of any monkeys, so we'll slap on that label. As you traverse this labeling journey, you'll watch the counts for your two labels grow. The aim? A bare minimum of 10 images for each label. Post-labeling, we've got 108 monkeyless video frames, 42 frames containing a monkey, and 9 frames deliberately left unlabeled. These unlabeled images will allow us to test our system with data unseen by the AI once we've trained our model. Want to look at the images with our monkey pals? Just click the label and you'll be treated to all those images. Vice versa, we can journey through the monkeyless images, revealing images devoid of any monkey antics. Now let's gear up to train a new model using AutoML with our meticulously curated dataset. The incremental training capabilities are worth noting here. If needed, this allows upgrading an already trained model with more data. Next, let's also set our maximum node hours for training. This is an important specification since node hours are the cost driver for AutoML. Let's open the Google Cloud pricing so we can see the price tag. Normally, cloud training is the name of the game with a cost of $350 per node hour. By adjusting the total node hours, we're impacting both the cost and quality of our model, since the training system will align the resources and training time to the provided budget. A few node hours can often be enough, but we'll demonstrate extensive and perhaps extensive training for a dataset of this size. The cost-quality trade-off will be quantified once we see the model's training metrics like precision and recall. For demonstration, let's lock in a 20 node hour budget. Some helper text below the field suggests how long training will take with that budget. Moment of truth, let's kick this off. The training will take some time. Sit back, take a sip of coffee, and relax. If your relaxation turns to panic because you realize that you misconfigured the training, worry not. Just head to the training section in Vertex AI and cancel the job. Voila! Looks like our model is ready, all trained up. Venture into the model registry, and there our AutoML trained model sits, shining bright. Instinctively, the first thing we'd want to review is the precision recall curve and training metrics. 100% precision and recall is usually a bad sign, a sign of overtraining. However, it's a small data set and we have some additional test images to validate. To improve generalization, you should strongly consider using multiple videos to train the model, and our frame extraction pipeline is built to handle that. But let's test our model without that. Remember, we trained using 150 images, leaving the remaining 9 for additional testing. To run those tests, we need to set up our model on an endpoint. For that deployment, we'll keep the node count low for cost reasons. Logging is typically advisable. Once more, let's wait a bit and snag an unlabeled image from our dataset for testing. We can plug the image files from their cloud storage links. Upload an image to test, and look at that. High confidence in the contains monkeys categorization. The flip side also works well. While we focused on the console today, your deployed model is of course also programmatically accessible. For example, access your model via its endpoint APIs in custom web applications. Thank you very much for watching, and we'll keep an eye on the comment section for any questions. Please enjoy responsibly.